Hi everyone, I'm Angad Yuvraj from University of Delhi, Department of Physics and Astrophysics. I'm doing my PhD under Sanjay Jain in the field of origin of life. And for the first session, we have speakers from the field of stochastic thermodynamics. I would like to welcome Professor Marathe, who is an associate professor at IIT Delhi, who will be giving the first talk.
Okay, thank you, and it's great to see you all after so many years. So today I will be talking about a heat engine, which is happening at a macro scale, and the title for my talk is Analytical Study of a Brownian Heat Engine in Viscoelastic Active Suspensions. And I'm at IIT Delhi, so this is the outline. So I will show derive a microscopic derivation of the generalized Langeva equation for an active system. And as an application, I will show how it is, what happens in active Brownian heat engines. And this is the work done with Antonio and Juan. They are in Mexico. And this is the paper which has recently published. So usually what you have is, we all know what are thermodynamic engines like Carnot or Stirling. But if you reduce the size of that engine to a single Brownian particle, then the fluctuations play an important role. And if you have a system where this is a passive Brownian particle, like a colloidal particle, which is trapped in a harmonic trap, and it is surrounded by the fluid molecules. And then they will just do a Brownian. So this particle will show a Brownian motion. On top of that, if you have certain active particles like Janus particles or bacteria, which are also suspended in this, then the dynamics of this changes quite a lot depending on how dilute or uh, what is the density of these active particles. And one of such example is basically this uh, motor. Yeah, one of example is this motor where bacteria actually rotated this wheel in unidirectionally just because of the asymmetry. So to model, what you usually have is a Langevin equation. This is an underdamped Langevin equation. You have a memory kernel, and there's this k of t is the external time-dependent potential, which is basically expanded and contracted to mimic what you do in a normal thermodynamic heat engine of moving a piston from from one place to other and taking it back. And you can make a Stirling or a Carnot cycle out of this. And there is this xi, which is the usual white noise, which satisfies the fluctuation dissipation theorem. This is the generalized Langevin equation. And if there are no active particles, then this is the equation that you have. It's a completely equilibrium system. But because of these active particles, this system is completely non-equilibrium. And as you can see, there's this active noise that is basically mimics the interaction of this particle with the active particles, breaks FDR, and it can have completely non-trivial correlations. So this is the fluctuation dissipation theorem of general fluctuation dissipation theorem of the second kind, but there is no such theorem for eta active, the active noise. I don't know why it's not. Okay. Yeah. So to model this, as I said, that this active noise can have non-trivial correlations. There are different kinds of models to mimic this active noise. There's something called as dichotomous process or a run and tumble trichotomous, which looks something like this. They flip between two states randomly, and then there is Ornstein-Uhlenbeck process. Which has Gaussian colored noise, but all these which model the active noise are phenomenological model. And what we plan to do is basically you start with equations consisting of the interactions between the passive Brownian particle, we call this PBP, and the active particles, the active Brownian particles, ABPs, and integrate out the degrees of freedom of these active particles, and if you can get a generalized Langevin equation after integrating this out. So this is very similar to what we do in this Caldera-Leggett kind of a model, but only thing is this is happening in a non-equilibrium situation because the system is out of equilibrium. So what you would start with is you start with a three-dimensional position of this passive particle. X, Y, Z are its limit, and in overdamped system you write down this equation, which is very similar to the Langevin equation with this noise and everything, which satisfies fluctuation dissipation theorem. And this is the harmonic potential, which is shown by this red parabola, and this is the interaction between the active particles and the passive particle. So I will not go through all the details, but these are the equations they look like. And we assume that the interaction between the particles is something like this. So it is derived from a potential. And we assume that the number of active particles in the bath are much larger than 1. And they are represented by these coordinates Ri. And as you know, there's some movies which were shown by Sanjib yesterday, that these active Brownian particles, they have diffusion along their direction. So they kind of do this and move in a directed fashion. So those that is represented by this equation, where V is the propulsion velocity and Ni is the unit vector which shows the direction in which this particle is moving. Okay, and they satisfy, again, this is a noise which takes care of the random diffusion in the directions, and they satisfy this, and we assume that there is no interaction between the two or any of the active Brownian particles among themselves. So that's our these are our assumptions. So what you do is you want to write down an effective equation of motion for the passive Brownian particle, and it looks something like this. And the problem is to find out this average GT, where average GT, the average corresponds to the average over all the degrees of freedom of the active particles. So you can write down this quantity, where this is the density of active particles conditioned that the passive particle is at position R. And we assume that the interaction between the active particle and the Brownian particle are harmonic. We also assume that this K, which is the interaction strength of the harmonic ABPs with BPs, is much less than this kappa, the external harmonic potential. So what you do to do this is you do a perturbation near R equal to 0, and then the first term is just Ri square, which is the harmonic potential of the, it's like a confining potential for the active Brownian particles, into this term, which is bilinear. So it will be something like Ri into R, Ri, right? It's like very similar to the Caldera-Leggett kind of interaction. And we use a method which was proposed by these people some years back to get the equation. So the thing is that you have to integrate out degrees of freedom, this Ri, and get an effective temperature, effective description. And this is the effective description that you get. And as you can see, this is the gamma, which is the friction kernel, which is the generalized Langevin equation. This T corresponds to the thermal fluctuations, and as you can see, the fluctuation dissipation theorem is satisfied because you get this gamma T minus S, and these are the correlations between the active noises, and they are quite non-trivial. And unlike earlier models, this is actually derived microscopically. Okay, and as you can see, there are several parameters and several time scales.
Professor, you have 2 + 2 minutes.
Okay. So now, so this is the first part of the talk. Now I want to apply it to a certain system, and we apply it to what are known as the active heat engines, and which are very popular. There are some amazing experiments done in Bangalore at different places. So what you do usually in these Brownian heat engines, they put this particle in a harmonic trap, and they expand and contract this trap in a way, and then they change the temperature from one part to the other. So it's not an isothermal engine, it's more like a they require 2 temperatures, and it's very difficult to control in an experiment. However, you can tune the activity of this or the propulsion velocity of these active particles by flashing lights or changing the chemical gradient and so on. So that's what we do. So this KT follows a certain expansion and contraction state, which is as usual, but we do not change the temperature at any stage. Temperature remains constant, temperature of the bath. But the propulsion velocity switches so it starts with V0, at half time it switches to 0, and at this stage is again switched on to V0, so that to complete the cycle, and it returns back to the original state. So you substitute this in the earlier equation and solve and take a Laplace transform, and what you get in the steady state is the mean displacement of the particle, the passive particle, and it looks something like this. So this sigma t square is nothing but the thermal mean square displacement, and this part comes from the activity, interaction with the activity. And this alpha is a very important parameter because it tells you, depending on the value of that alpha, whether it's a crowded environment or a dilute environment. So for alpha equal to 1 or close to 1, you will see that you recover your normal thermal part, and when alpha is equal to 0, the active part dominates. So these are some parameters, so I don't have much time. So you define your work done and heat done, because work done will be nothing but the area under this cycle, and you continue this. And so these are different time scales in which you have to study this system, and the behavior is completely different. And this is how the efficiency look like. It turned out that the efficiency of these active engines surpasses that of passive engines, and we see many different different scenarios depending on those parameters. So the summary and conclusion is that a microscopic derivation of the generalized active Langevin model is presented. Using this, we analytically calculate efficiency of a Stirling-like isothermal active engine. Isothermal is important. So viscoelastic relaxation time of the active suspension reduces the efficiency, unlike which was seen earlier. And non-Markovinity is the main cause of reducing this efficiency. And there is a time scale which is involved in the friction kernel and the active noise-noise correlations, and it's a competition between these two time scales. And depending on that, it might reduce or even increase efficiency. And with this, I would like to thank you very much.
Okay, we can take one quick question.
Why would you expect the interaction between the passive particle and the active particles to be a simple harmonic oscillator kind of thing? Because you would be expecting it to decrease with distance instead of like increasing with distance between the particle and the active particle, right?
Sorry?
The interaction between the passive and the active particles, you would be expecting it to decrease with distance instead of increasing with distance, as is for a harmonic oscillator that you assumed. You have assumed a harmonic oscillator interaction between the passive and the active.
Yeah.
But you would be expecting them to decrease. As you go away, the active particle goes away, you would be expecting the interaction between the passive and the active particle to decreease, right?
Yeah. So, okay. So this is the, I mean, but the thing is that it depends on what kind of, how many, okay. So what is the density of these active particles? So it's like that even if the one particle goes away, there are several particles which are surrounding it. So effectively, this particle will always get affected by all this. So this is like the simplest interaction you can have. So that's basically the model. Of course, you can put this complicated interaction, but then the analysis doesn't really become so simple. We could actually integrate this out using this interaction. But
that is what you do in the FTR also.
Yeah, exactly. But this is a standard interaction also used in normal statistical to derive a Langevin equation, which is equilibrium.